All right, folks, today we're going to talk about work, power, and energy. So the first question that's proposed here is asking what is work? And work is simply force multiplied by distance. And just remember that we measure force in newtons and we measure distance in meters. So when you do multiply this out, you get a Newton meter, which is also known as a joule. So the joule is the basic measurement for work and energy. You will see that work and energy have the same units because in essence they're measuring the same thing. One thing to remember when we're calculating work, force and distance have to be collinear, or they have to be going parallel to each other, so they need to be going in the same direction. So there may be applications where we talk about pushing or pulling on an object, but you may be applying a force that's not in the same direction the object's moving. You may have to use a little bit of trigonometry in order to figure out what that force is in the direction that the object's moving. And I'll have a couple of examples here that will show you kind of what I mean. But to keep it simple for starters here, example number 1 simply says a person applies 10 newtons of force in the horizontal direction to slide a box 5 meters across the floor. How much work do they do? Well, if somebody literally has a box and they're pushing it this direction with a force of 10 newtons, and they're going to move it total distance of 5 meters across the floor, we can simply multiply the force by the distance that they travel, and we're going to get the work. So, just like solving most physics problems, you want to list the variables that they give you, as simple as work, force, and distance are. Still list everything out because as we get a little bit further along, things get a little bit more complicated. So, let's just take the force they give us of 10 newtons. We say it's going to travel a distance of 5 meters, and the work is the unknown. List the equation that you're going to use. Work is force times distance. Take your 10 newtons and your 5 meters. And 10 times 5 will give us 50. And again, if you remember our units, a Newton meter, again, is the same thing as a joule. Example number 2, we have a very similar example, except now the force is going to be applied in a direction that's not the same as the direction of motion. So they say in the example that a person's pulling this box across the floor, they're applying 100 newtons of force along, let's say it's a rope or a chain or something like that, or a handle. It's an angle of 15 degrees above the horizontal. How much work is done if the box slides 3 meters? So again, the direction of motion for the box is perfectly horizontal, but they are pulling at somewhat of an incline above the horizontal. So we need to do a little bit of trigonometry in order to figure this out. Work is still going to be force times distance, but we need the force this way. We need the force in the x direction if we're going to multiply it by the distance in the x direction. So our work equation is still going to be pretty simple. It's still going to be work is force times distance. We'll say it's f of x times d of x, but we got to do a little bit of trigonometry here to figure this out. So I'm going to just redraw the triangle. We've looked at this in the past. We'll say we have 15 degrees here. This is going to be our f of x, this is going to be our f of y. We don't necessarily need to know our f of y, but we do need to know the f of x. So the equation for this would be equal to the hypotenuse of 100 multiplied by the cosine 15 degrees. And if I multiply that out, plug this into a calculator, make sure you have it in degrees and not radians. This will give me 96.6 newtons in this direction. If I do the multiplication for the vertical component, you would do 100 times the sine of 15 degrees. So instead of cosine, we'd have sine, and this would give me 25.9 newtons. So while you're applying a force in this direction, part of it's vertical, part of it's horizontal. The vertical part is really wasted effort because the box isn't moving vertically, it's only moving horizontally. So this is the value we use for force in that direction. So I'm going to use my 96.6 newtons, and I'm going to multiply it simply by the 3 meters that the box travels in this direction. So now that they're going in the same direction, we can simply say that we got 290 joules worth of work that was actually put into it. Okay? The next concept we're going to look at is what is power, and I'm sure you guys have seen or heard of power radians, whether it's on light bulbs or microwaves, or you hear things about power company or whatever it may be. Power is a rate at which you consume energy, or the rate at which you do work. So if you did a certain amount of work in a certain amount of time, we could take that power, or sorry, to get power, you could take that work and you could divide it by that time. So the standard units again are still joules for work and time for seconds. So when you get done, you get a joule per second, and a joule per second is also known as a watt. Here, we're going to take the information that they give us. Person's picks up a box doing 100 joules worth of work, and it takes them 4 seconds to do this amount of work. There's the 4 seconds, and they ask us what is the power. Well, again, list your equation. Power is work divided by time. If the work that they give us is 100 joules, and the time that they give us is 4 seconds, you can simply take 100, divide by 4. This is going to give us 25 watts. So the concept of that, it's more difficult typically to find the work put in, because again, we could be moving things at angles or picking things up that are only given masses and not forces. So a lot of the work for power ends up, a lot of the work, so-called academic work that goes into it, happens with calculations for work. The time is easy. If they give you time, you just simply divide the work by the time and you're going to get the power. Okay? Then we're going to talk about two basic forms of mechanical energy, potential and kinetic. While energy can come in a lot of different types of forms, it can be either stored or it could be in use. So in the world of mechanics, or things that are moving, we would say things have gravitational potential energy, which is based upon their weight, which is a force, and the height that they are above what we're considering to be ground zero. So if something has the potential to fall or slide down an incline, we would say it has potential energy. And anything that's in motion, we also say it has energy, and it's equal to 1/2 mv squared. But if there's no velocity, then that type of energy wouldn't be present. How do we calculate gravitational potential energy? The equation up here says mass times gravity times height will tell us potential energy. So we simply want to list all of our variables, and then we'll solve for the unknowns. So what do they give us in this situation? A 10 kilogram box is sitting on a 10-meter cliff. So we have a mass of 10 kilograms. We have a height of 10 meters. The potential energy is unknown. One thing will commonly not be listed in these problems is the acceleration of gravity. It's one of those kind of constants that, as long as we're on Earth, we would know that we're dealing with the value of 9.8 meters per second squared. We know potential energy is equal to m times g times h. So let's plug in everything we got. We know that the mass is 10 kilograms. We know that the acceleration of gravity is 9.8 meters per second squared. And we know the height that this object is from the ground is equal to 10 meters. So if we do 10 times 9.8, we get 98, and if you multiply that by 10, we get 980 joules. Now, how do we calculate kinetic energy? Kinetic energy has a different equation, even though it's measured in the same units. It's still measured in joules. However, we measure kinetic energy with a value of its mass and velocity, and then plug it into an equation. So when you're solving just kinetic energy problems, they need to give you a mass, which in this situation is 10 kilograms, and they give us a velocity that's equal to 5 meters per second. The unknown here is kinetic energy, so I'll list that as the unknown. The equation, if we want to list it out, kinetic energy is 1/2 mv squared. So there's only two variables here, but there is a square and a fraction in there. Just remember, when we plug in and solve for our values, the 1/2 times the mass, 10 kilograms, and then the velocity squared. This needs to be squared before we multiply or divide. So I do 5 times 5, which gives me 25. 25 times 10 gives me 250. And then if you take half of that, this is going to leave me with $1.25 here, 125 joules worth of energy. All right, for example 6, this is taking a little bit of application for potential and kinetic energy, and it's applying it to a roller coaster scenario, which is a pretty traditional application in the world of physics when we talk about potential and kinetic energy, potentially work and power. I show a cart on the roller coaster in 4 different locations, and I will disclose a mass of the cart, and I'm going to tell you the height above what we're going to consider 0 to be, which will be down here at C. We'll give that information, and then we're going to want to calculate what is the potential energy and or kinetic energy, and maybe even the velocity. We'll go back and kind of flip some of these variables around and see what we got. So first analogy is saying that the cart is at the top, the highest hill, and this is going to be at a height of 10 meters. So when I look at it here, if I measured from here down to here, we'd be saying that this is at a height of 10 meters. And in location B, going from basically here down to here, we say that this is at a height of 4 meters, and the cart in position C is as low as we're going to go, which we're going to consider to be 0 meters, and then the location from here down to the bottom here is at a height of 5 meters. Now they're going to ask for some different things about this. For position A, B, and C, they want us just to find the potential and the kinetic energy. For position D, they're going to just give us the height, and they're going to ask us to find the velocity. So here's a couple of things to understand. The total amount of energy in a system, in a closed system, is always the same. So when we look at this whole thing as a system, there was a certain amount of work that had to get put into this system to get the cart to the top. It didn't lift itself from the ground to here. And if you were riding a real roller coaster, if you remember at the beginning of the ride, the first thing that always happens is you get hooked up to a little chain, and you can hear all the clicks going up and up and up and up and up. There's an electric motor in here, pulls the chain, puts all the work into the coaster. Once it's here and it falls and goes up and down all the rest of the hills, it's using all of the conservation of energy from this. It loses some energy to friction as it rolls around on the track and the air passing by. But that's the only work initially, or the only energy put into it initially, is just that first portion. So if I start here with 1,000 joules, when I'm here, I still have 1,000 joules. I have 1,000 joules here and 1,000 joules here, if none of the energy is lost to friction. And in our analogy, we're going to assume that this is a frictionless world. So there's no friction on the track, there's no friction in the air. So this is going to, there's no friction on the track, there's no friction in the air. This is going to consume it, or going to conserve its total energy the whole time. With that said, when we do our initial energy calculation at the top, that's going to be our full value of energy. And as we go down, we're going to need to always have potential and kinetic energy added together to equal that same value. So at the top, it's all potential. The cart at the initial point here, we're going to assume is not moving. And at the bottom, we're going to assume that it's all kinetic. There's no more potential here because it can't fall anymore. So the energy here, 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 and here will always equal that same value. In some places in between, at position B and D, there will be some potential and some kinetic. So I'll show you how we can determine that. So first thing we're going to do is figure out, well, what is our baseline? Well, if we want to figure out the potential energy of the cart when it's at its highest point, we simply do m times g times h. So the mass times the gravity times the height. So we know that the cart is equal to 100 kilograms, and I'm neglecting the units here just to save some space, but it's 100 kilograms. We know the acceleration of gravity is equal to 9.8, and the height that it is above the ground here is equal to 10. So if I multiply the 10 times 9.8 times 100, this gives me 9,800 joules. Now this is an extremely important number because at the top, assuming that the cart's motionless before we let it go, that's the total amount of energy of the system. There's no kinetic energy before we let the cart go. So in the problem, they're saying at the top, let's assume that the velocity is 0 and it's a frictionless world. Now for part B, we're looking at what is the potential energy and kinetic energy when it's 4 meters off the ground. Well, the total is always going to equal this, but we want to figure out how much of it's still left in stored energy, or potential energy, and how much of it's going to be left over for kinetic. So if I do the mass times the gravity times the new height, it only has 4 more meters to fall. It doesn't have the full 10 to fall. If I multiply that out, I get 3,920 joules. Now, if we knew the velocity, and if I went through and did some free fall acceleration problems or applications here, I could figure out what the velocity is, but the easiest thing to do to figure out the kinetic energy, you just find the energy by difference. The total has to equal 9,800. I've already consumed or have left 3,920 joules. So what's got to be left over to get me to that grand total of 9,800? It's 5,880 joules. So there's more energy in its velocity than what's stored. So the potential for it to continue falling and picking up speed. When we get to the very bottom, the potential energy is equal to the mass times gravity times the height. Well, the height at the bottom is 0, so this one, bam, goes right to 0 joules. And the kinetic energy, again, assuming we have a frictionless world, frictionless surface, all of the energy from the top has to be present at the bottom. It's just been transformed from potential all to kinetic. So there's the total amount of energy still left in the system. The next part of this is going to ask us how to apply some of these concepts in a little bit of reverse. So it's asking, what is the velocity of the cart at point D if the height is 5 meters? So they want the velocity here. Okay, well, I can figure out a couple of things about this. If we're going to figure out the velocity, we're going to be looking more at the kinetic energy. So I want to figure out the kinetic energy at this point. Now I know it's halfway from the top to the bottom. I could make the assumption that it has half of the energy that we started with, but just to prove our point, I'm going to simply solve for the potential energy first, and then I'll kind of reiterate or show what we got left. So if it has 5 meters left to fall and it started at 10 meters tall, we know that the height is 5 meters. So my potential energy here is going to be equal to the 100 times 9.8 times 5, which is going to give me 4,900 joules. Now, since the height is the same left to fall as what has already fallen, and the 4,900 is exactly half of our 9,800 that we started with, I also know that the kinetic energy here is going to be equal to the same thing. It's going to be equal to 4,900 joules. So how does this help me find the velocity? Well, our kinetic energy equation has the variable of kinetic energy, mass, and velocity. Well, we know the kinetic energy, we know the mass, and we want to find the velocity. So, just like most equations, they can be rearranged to solve for different variables. So if I multiply both sides by 2 to cancel out the 1/2, divide by the mass, and then take the square root of everything to get the v by itself, I get an equation that looks like this. It's 2 times the kinetic energy divided by the mass, square rooted, equals v. So, plug in the values that we got. 2 times 4,900 here. The mass is equal to 100. Square root it. And this will now tell us our velocity at that point. So if I do 2 times 4,900, that gives me 9,800. 9,800 divided by 100 gives me 98. And if I take the square root of 98, I get approximately 9.9 meters per second. So that would be the velocity of the cart at this point right here. So again, the most common thing you got to remember with energy is it can never be created or destroyed. It is always transformed from one point to another. So simple application, taking a look at the roller coaster. Just remember in the real world, sometimes people ask, well, in the real world it doesn't work that way. The energy is not conserved. The roller coaster slows down. It doesn't continue moving forever. That is true, but the energy isn't completely lost. It's just transformed into its surroundings. So when you hear the roller coaster making noise, and you can hear the wheels chattering and the clicking and the grinding and going around, the whoosh of the air, all of that stuff consumes energy. Friction creates heat. All of those types of things are energy. So they're taking energy away from where that electric motor originally had put it into the system. And it's always accounted for. It's out there somewhere. If you consider the area that the cart is in to be your closed system. So for the last part here, I got a couple of examples of kind of putting it all together. So we're going to look at work, power, and force, and how to solve some kind of basic simple work, power, energy problems. So what we got in this first one here is an electric motor connected to a frictionless pulley, which is suspended a 200-gram mass. And the question is asking how much power will the electric motor use if it lifts the 200-gram block a height of 4 meters in a time of 5.6 seconds. So ultimately they're asking us to find power, but before we can find power, we got to find work. do not be confused what force is. Force is a weight. Mass and weight are not the same thing. In this problem, they do not tell us the force. All they tell us is the mass of this item, and the mass that they give us is not in kilograms, it's in grams. So if I'm going to create a force out of this, force is mass times gravity. 200 grams is the same as 0.200 kilograms, or just 0.2 you could put. And the distance that this object travels going upward is 4 meters. So this is a mass. If I multiply it by 9.8 meters per second squared, this turns into a force. So the combination of this multiplied by this gives me a force or a weight. If I want to add the distance in here, I got to multiply all of this by 4 meters in addition to just to get the work. So if I do that, if I have the 0.2 kilograms, that's our mass, multiplied by the acceleration of gravity, 9.8, and multiply that by 4, I get a value for work of 7.84 joules. Once we get work, again, a lot of the effort, the academic effort going into finding power is always to calculate work. Well, we know we got 7.84 joules, and the time that they give us for the motor to do this is 5.6 seconds. If you divide 7.84 by 5.6, I get approximately 1.4 watts. Next example, it says, assume we have a ramp, and this ramp is going to be frictionless for sure, at least for the boxes. We'll assume that the shoes that the girl is wearing are not frictionless, so she can walk up it. It says, assume that the man who's over here not using the ramp, let's say he lifts a rock straight to the top of the ramp without using it. He just picks it up a distance of 2 meters. The girl, on the other hand, is going to use the ramp, and she is going to push the block up the ramp, and that's at a length of 3.2 meters. With this, assuming that everything's frictionless, we're going to try to answer some of the questions down below. Now they're broken up quite nicely. They're trying to break these into pieces so that we can more easily solve for work or power. So question number 1, how much work did the man do? Well, work is simply equal to force times distance. The mass of the block is given to us, and the mass again is equal to 5 kilograms. Remember, mass is not force, mass is not weight, mass is just mass. So we got to do the 5 kilograms multiplied by the 9.8 meters per second squared, then multiplied by the distance of 2 meters, all of that just to get the work. This ends up being 98 joules. So the man picking the block straight up into the air, no friction, not using the ramp, does 98 joules of work. The girl is going to push the block to the same height. She's going to lift 2 meters, but she's got to push 3.2 meters across the ramp. Well, one thing that ends up being a perfect trade-off here, and it's kind of interesting how this works, simple machines, they don't make you use less energy, they just make work easier to do. So this guy, yeah, that might be a little bit difficult as far as the strength required. Might take more strength to pick that straight up than using the ramp, but at the end they're going to do the same amount of work. Let's see what we got. We got force times distance. They say that the girl has to apply 30.625 newtons to the block, and this is already in a force, so we don't have to convert that, and she pushes it a length of 3.2 meters. Now this is, just to kind of point out, this force, 30.625, is less than the 5 times 9.8. This will give you, approximately 50. So you can see she applies less force, but she's got to apply it over a greater distance. So instead of 2 meters, she's got to apply that force over 3.2 meters. When you multiply these out, you get the exact same amount of work. So it doesn't really matter if you're using the simple machine or not. The amount of work doesn't really change. It's how easy it is to do the work. So you'll find there's a trade-off, whether it's inclined planes, levers, pulleys, wheel and axles, a lot of that stuff. It's just a trade-off force for distance. So if you have less force, it's going to be more distance. Letter C, how much power did the man use if he lifted the box in 1.4 seconds? Well, again, power is work divided by time. So we know that the man did 98 joules of work, and they're saying 1.4 seconds for his total time. So if we divide that out, we get about 70 watts of power. And then the woman here, they say that the power there still work divided by time. She also did the same amount of work, but she's going to take a little bit more time to do it. She's going to take 5.3 seconds. 98 divided by the 5.3 gives me 18.5 watts. So, the power, even though the work was the same, they both did the same amount of work, the one who took more time to do it used less power. All right, folks, that's about all we got for the notes for today. There'll be a lot of other work for this week, but make sure you guys have these copied down and ask questions if you need. Otherwise, use this as a resource. Go through the examples so that you guys have some baseline to look at. A lot of the other assignments are kind of based on these concepts. So thanks a lot, and you guys have a good week.